Okay, I'm going to go ahead and just knock out the rest of this final. There's only one where it kind of stumped us a little bit. So I think we just showed in the last hour the 2,000 kilowatt hours for the month. Wind blows more at night when electric requirements and wholesales are low. Okay. Which strategy best describes a method to store energy when wholesale prices and electric loads are low, and resell the energy when the prices and loads are high? Arbitrage. We call it arbitrage. Frequency regulation? Not really. Maybe. Okay. Calculate. Sorry, that's kind of annoying there. Calculate the monthly cost for this electric service. 6 cents per kilowatt hour. Let's just check this out. Let's check it out. K-bar. Insert. Text. Insert text box. Okay, so there's going to be your kilowatt hours per month is 683,000 dollars per kilowatt hour, 0.06 dollar, comma. This is going to be our energy. Cost for energy equals kilowatt hours, dollars per kilowatt hour. Dink, 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 dink. It's a nice little output there. These are both inputs. Okay. $12 per peak kilowatt month. So dollars per kilowatt month, 12. Kilowatt month, 100. Dollar for power. Dink times dink. 45 cents per peak kVAR month. Let's want to do a little calculation, so we'll leave some money here. So dollar per kVAR month. $0.45. Okay, save that. 65% power factor. So here we're going to have to just figure out the so power factor. Power factor 0.65. Save that. Give me a second. Okay, so I'm running this guy right now. Go back to the problem. So we're going to pay for power. So we're going to pay for power, energy, and kVAR. So energy is straightforward. It's just the true power, true energy, times the cost per kilowatt hour. Here's our demand for power, so we're going to have to spend $13,200 a month for power. We've got demand charges $12 per kilowatt. And then I went ahead and I just calculated the average power coming out of the system. Total kilowatt hours divided by hours in a month, so that's our average power. Here's our power factor. So these two guys are both given. Put those in yellow. Average power, that was calculated. We'll put that in blue. And so then I just came up with sort of an average KVA, which is the average power divided by the power factor. So the KVA is always going to be greater. In this case, it's significantly higher. It's a very low power factor. So that's also calculated. So then our kVAR is just the Pythagorean theorem on the true power and the kVA, parent power. And then the dollar for the kVAR is the cost per kVAR times the kVAR that we just found. So that can also be in blue. And then this guy is the sum of all three. Total bill. There we go. So 54.6, and I'm going to do this, equals ceiling of that divided by 1,000, comma, point, significance, 0.1. 54.7, let's see if we got that, 50.87, so closer to 6 or to 7. Let's give it 0.01 significance. All right, so it's closer to 6 than it is to 8. Try that. Okay. Consider a strip chart showing the grid's frequency measurement displayed over a period of time. When the frequency slope is positive, frequency slope is positive means electric load is below, less than. So the frequency is humming along at 60. As soon as if the load goes down, the frequency goes up. If the load goes up, the frequency comes down. Try that. Depending on its application, energy can be stored as, depending on its application, energy is stored as select 1. Distribution asset, yeah. Could be a load too. It could be a load. Electric residential water heaters can be controlled to help manage frequency on the grid. Oh yeah. Turn them on and that'll dink the, okay. Utility offers incentive for a customer for a project that saves 150,000 kilowatt hours per year and has a project cost. Let's just see if we can bust this out really quick. Copy that. Pause this. Okay, it's late. I'm tired. I'm going to take a little bit of a break, but yeah, these next few I'll just go through them and we'll cover them. So this next one is looking at levelized cost, and I started digging into it. There's kind of a lot going on here. So annual savings is 150,000 kilowatt hours. There's the cost. You're going to run it for 15 years. energy is 7 cents per kilowatt hour. Incentive based on the lesser of 12 cents per kilowatt hour per year, or 70% of the cost, which would be $35,000. Utility discount rate is 6.5%. So I had an annual savings in dollars of the rate, which is 7 cents times the energy. So you're going to save that many dollars per year. This guy is the incentive, 12 cents per kilowatt per year, that's the incentive. And this is where it gets a little tricky. I was trying to figure out the present value. If you're saving $10,000 a year for 15 years at a discount rate of 6.5, and I got down into the weeds a little bit. We'll finish that one off. Next, that's probably, I'm just going to take a shot at it. Aim in the middle. Actually, it was coming up with, I think I just had an error somewhere. Homeowners received a bid for $8,000 to install a 1.5 kilowatt PV system. The utility is going to buy it from the homeowner. Utility will pay the homeowner each year for 15 years at a rate of 25 cents. The expected generation is 110 kilowatt hours per kilowatt DC for 15 years. The PV system is estimated to have a residual salvage value of $2,000. The owner uses this. What's the present value? Okay, so we can do that. That's a good problem. We'll do that on Thursday. 2,000 CFM oil flooded rotary screws operating at full load. Compressor uses a valve to regulate airflow. When it's closed, the compressor is still using 65% full power. Compressor delivers airflow of how much CFM? Okay, so we'll use our affinity laws there, 17. What is the annual electric cost for this pump? Oh, so here's here's your cents for energy, kilowatt hours. You're using it 80-30% of the time, 1,400 gallons per minute, 108 PSI. There's the efficiency, motor efficiency. Okay, we'll do that. Motor and pump, so it's the product of those two. Cool, so 90% of 70. Get that. You're walking across a river. How many thousand will it take to, oh, that's a good one. So the generator, okay, we'll do that one too. A pump is supplying water at 150 GPM using the affinity law. How much power? Okay. Okay, so we know what we're up against. Anyway, I will see you Thursday. Thanks for your attention.